All right, so this chapter we're going to be discussing some more carbonyl chemistry, and specifically condensation reactions. So there's a few named reactions, and those are going to be aldol, either aldol condensation or aldol reaction, as well as Claisen, the Diekman and Michael, and the Robinson annulation reaction. So a lot of this chemistry is kind of piggybacking on stuff we already know. So it's just going to be some enolates reacting with some nucleophiles. With some electrophiles, or nucleophiles reacting with carbonyls. So remember, nucleophiles reacting with carbonyls forms it forms the addition product, which would be the new alcohol. And in addition to that, ketones, or anything with an alpha hydrogen, can be deprotonated to form an enolate that reacts with an electrophile. In addition to this, if we have a Z functional group where Z is a good leaving group, we can form a nucleophilic acyl substitution product where the nucleophile substitutes that Z. So the first two are going to be related to the aldol reaction. So let's say we had an aldehyde and another aldehyde of the same structure, and we have them in the presence of hydroxide and water. Well, what I want to do is highlight the various hydrogens in the two of the same structure, aldehydes, but we want to focus on where these are going to end up in the end. So the hydroxide is going to remove the alpha hydrogen to form the enolate, and that enolate, remember, is the nucleophile that can attack an electrophile. So we're combining the two of things that we've already done before. So we've done nucleophiles attacking carbonyls, and we've done enolates attacking electrophiles, and now we're just kind of jamming those two together. And so once that happens, we form a tetrahedral intermediate, and then we protonate that with water, and giving us this beta hydroxy carbonyl product. And I've highlighted the protons in red and blue just to show you where those ended up and how we pretty much just jam those two aldehydes together, forming an alcohol as well as an aldehyde. And that's where the aldol name comes from. It's aldol, as in aldehyde and alcohol. Note that the hydroxide forms a small amount of an enolate, so it's actually working out well for us in this sense, because since we have two of the same aldehydes, we don't want a large amount of the enolate forming, because then we wouldn't have enough enolate or enough aldehyde around to act as the electrophile. And so this does actually work out in our favor. So an aldol reaction can also occur with aldehyde, and other than aldehydes, it can occur with ketones as well. And so it's important to note also that the products are favored when you do aldol condensations with aldehydes, whereas they are not favored when you do them with ketones. And so we kind of have to get creative in driving those reactions forward. So let's take a look at an example. We have this particular aldehyde here. We remove the alpha hydrogen to form the enolate, and this enolate reacts with another molecule of itself. And I've abbreviated the benzene ring in two different ways. So in the first structure, I wrote all of the double bonds, and then in the second one, I just drew a circle. That's to show that those double bonds are conjugated. And then the third, I just drew a phenyl pH. So just to remind you guys of the abbreviations to make mechanisms easier for you guys. So once that enolate attacks the aldehyde carbonyl, we have and then we protonate it, we form the beta hydroxy carbonyl. And that is the structure drawn above. So it can get a little tricky when you're drawing out. It gets a little tricky when you're drawing all those new carbon-carbon bonds. That's one of the great things about aldol condensations, that you do form new carbon-carbon bonds. So that's the great thing about synthetic chemistry, but you're also making it very complicated to draw those structures. And so it's important to just maybe color code them if you need to keep track of those, and that might be the best thing working out for you guys. So pause it, take a look at this structure, and see what kind of aldol product you would get. So basically we have benzaldehyde, we have hydroxide and water. Those are definitely something that we could use for an aldol reaction, but remember that the first step in an aldol condensation or aldol reaction is the removal of the alpha hydrogen to form the enolate. And in this case, we do not have any alpha hydrogens. So no alpha hydrogens, that means that there's no enolate forming, and that means that we are not getting a reaction. Okay, so it's important, obviously, know the mechanism. That way you can kind of jump to the product and get comfortable with doing the mechanism to get to the product, as well as just jumping straight to the product without even having to draw the mechanism. So the next portion of the aldol reaction would be a dehydration of the beta hydroxy carbonyl. So let's say we had this structured. This is one of the structures we made above. And dehydration is, just like in our bodies, the loss of water. So if we lose one molecule of water from the structure on the left, we end up with this alpha beta unsaturated carbonyl. And so this is definitely one of those ways that's going to help us drive the reaction forward in terms of the production of a desired product when it came to ketones, reacting with ketones in an aldol condensation. And this only works for beta hydroxycarbonyls, and so it's important to kind of double check to make sure that OH is actually beta to the carbonyl. And so let's go over the mechanism of a generic dehydration reaction, so that way we can kind of get an understanding as to how this works out. There are some small things that we need to kind of point out that aren't really as expected according to the other chemistry knowledge that we have. So once we remove that alpha hydrogen, we form the enolate. We react, in this case, with another aldehyde, and we get a beta hydroxy carbonyl. Okay, so if there are still hydrogens present, alpha hydrogens present, and so those alpha hydrogens can be removed by excess sodium hydroxide or excess hydroxide. So if we have excess base, we can remove that to form yet another enolate. And in this case, that enolate, the negative charge on that oxygen, if we kick that back down to form the carbonyl carbon, the carbon-carbon double bond can actually go over to form another carbon-carbon bond and kick out hydroxide as a leaving group. Yes, hydroxide as a leaving group, el terrible, right? That's not a good leaving group. However, in this case, it's going to be okay because we have the stability of this new alpha beta hydroxy carbonyl forming, and it's conjugated, and so this kind of helps overcome that undesirable OH leaving group. Another thing we want to mention is that this is a reaction called E1CB, and it's basically like an E1 reaction. However, it's an elimination unimolecular, but the CB stands for conjugate base, because rather than having a carbocation intermediate, we have an anionic intermediate. And so that's why we have E1CB. Other than that, they are pretty much they're the same idea. Okay. All right, so now let's put some of this knowledge to work with a little bit of practice. So let's see what we've got here. Let's try and identify what the product will be with this particular substance in the presence of hydroxide and water. So what we want to do first is note that this is a beta hydroxycarbonyl, and so we have that alpha hydrogen that can be removed, and technically the best mechanism to draw for this would be the enolate forming, and then it comes down to kick off that hydroxide. But short form, I can just draw the removal of that alpha hydrogen to form a carbon-carbon bond, and then the loss of that hydroxide to form the alpha-beta unsaturated carbonyl product. It's honestly, if you draw it like that, it's pretty much just an elimination reaction, and we know this stuff. So let's take a look at this guy. What's going to happen? Pause it and replay it when you're ready. So obviously this is not a beta hydroxycarbonyl, and so we actually don't get a reaction. It's not alpha beta hydroxycarbonyl, so we don't actually, if we were going to lose that hydroxide, that carbon-carbon double bond would not be conjugated with the carbonyl, and therefore we don't get that additional stabilization from the conjugation. So loss of hydroxide, not an option in this case. So let's take a look at this reaction where we have a cyclopentanone times 2. So we got 2 of these guys in the presence of sodium hydroxide and water. Now, what's going to happen? So the aldol condensations that we've gone over were aldehydes, right? But I did say that we can do this with ketones, and we can do this with 2 of the same ketone as well. And so the same mechanism to start as anything else, removal of the alpha hydrogen to get the enolate. That enolate is the nucleophile, and the carbonyls are the electrophile. And so that nucleophilic enolate is going to attack the highlighted blue carbon of the carbonyl, and we will ultimately break that carbon-oxygen double bond and protonate that to form the beta hydroxycarbonyl. And that's going to be pretty much just the 2 5-membered rings jammed together. Protonation from water is going to give us ultimately that beta hydroxycarbonyl. All right, so remember, in the presence of additional base, we can do an elimination reaction to get rid of that OH. I want to remind you that ketones don't favor the products, but this particular step right here, removal of that alpha hydrogen, which needs to be there in order for this to happen, will ultimately remove or eliminate that hydroxide to form the alpha beta unsaturated ketone, and this you can't come back from. So that's going to drive the reaction forward, and I'm going to highlight these in red just so you can see how the 2 were put together. So we have the starting materials on the left, on the bottom, and then the products on the upper right. And so visualizing it like this hopefully can help you understand and quickly jump from the starting materials to the product without having to work out the mechanism. Let's take a look at this new ketone combined with benzaldehyde. That's what the pH and the carbonyl are, with sodium hydroxide and water. So the benzaldehyde, note, does not have any alpha hydrogens, so that is not going to form an enolate. The enolate comes from that ketone, which can attack the aldehyde and give us this final product here. If we remove that alpha hydrogen, we form this enolate, which can then attack the carbonyl carbon. Ultimately, what that's going to form is the beta hydroxy carbonyl. After protonating the oxygen with water, once we protonate that with water, the additional base can remove that alpha hydrogen and eliminate the hydroxide to form this alpha beta unsaturated ketone product. Again, I've highlighted them in red just to show you how the two come together. Essentially, that carbon-oxygen double bond is replaced with the carbon-carbon double bond, and the oxygen is omitted. So what we want to do is think about that oxygen being gone, and then a new carbon-carbon double bond forms between the original carbonyl and the alpha hydrogen that forms the enolate. Alright, so let's take a look at this particular alpha beta unsaturated ketone and work our way back. I got a retrosynthetic arrow there, and that we want to know what starting materials we had to form that product. And so we know that the alpha hydrogen forms a carbon-carbon double bond. The alpha carbon forms a carbon-carbon double bond where an original carbonyl was. So what I've drawn in red is now going to be the carbonyl, and that's formaldehyde, and the rest of it drawn in green is just going to be the ketone starting material. So there you go, formaldehyde and cyclopentanone as the final product. All right, so let's try another example, and that would be, let's just draw that out here. I'm not going to name that. What do you think this came from? So let's pause it, whatever you got to do to try and figure this out on your own. I'm going to highlight this portion in red because I know that this alpha this alpha beta carbon-carbon double bond is coming from the original carbonyl group, and so this is more or less just how I break it down in terms of quickly jumping to the product. So we've got this benzaldehyde as well as cyclohexanone as a starting material. We can see that these last three reactions were actually between all different, either a combination of ketones and aldehydes, or ketones and ketones, and so, but different is the point I want to make. And so those are all unsymmetrical aldols, and these are also known as crossed aldols because they are not between two of the same carbonyl groups like we originally saw when we introduced the reaction. So, alright, so when it comes to unsymmetrical aldols, it's also important to note that only one carbonyl can have alpha hydrogens. Otherwise, you're going to get a mixture of products, and this is not synthetically useful in terms of money and atom economy, etc. So it's just a waste of time. If you put in 4 grams of material and you only get 1 gram out of a product that you actually want, that's a waste of your time. So there are ways we can overcome this, but one of them obviously is to use materials that don't have a variety of alpha hydrogens. So here we go. I'm drawing out a couple different reactions for you. By now, I think or with a little bit of practice, we should be able to just jump straight to the final product. The enolate is the one that's going to have the alpha hydrogens, and so that is the nucleophile and attacks the aldehyde carbonyl, in this case on benzaldehyde, and you can see that the structure of the nucleophile it looks the same in the product. You can still see that we have a hydrogen bound to a carbonyl, bound to a methyl or another carbon group, and so that component, the nucleophile, is still obvious in the product, whereas the electrophile looks a little bit different. In this case, it's obvious because there's a benzene ring in there, but the carbon-oxygen double bond is gone, right? And so in that sense, this structure is very different. And so it's just going to take some practice for us to visualize this and kind of quickly jump to the final product when we're doing these types of reactions. So let's try another reaction. Similar looking. However, we've got a longer carbon chain on the aldehyde. So we're going to start with the same relative skeleton of the final product. But what we want to do is count out the number of carbons on the aldehyde and then make sure that's what we have in the final product. Remember, the alpha carbon on the aldehyde is what does the attacking, and so that's what's doubly bound to the carbon on the electrophile, and then the rest of it is just the chain coming off of it. And so now what I want to do is give you kind of some examples of why the only one of the carbonyls can have alpha hydrogens, because again we'll get a mixture of products, right? So let's say we had these two aldehydes, and what we can do is either one of these aldehydes can react with as the nucleophile and attack the other, or it can attack another one of itself. That's two different things. Or that same aldehyde can act as an electrophile and get attacked by the other one. And then that ultimately leads to 4 products. And so I tried to highlight these 4 products in colors. So red and blue represent the starting materials on the left, and you can see that these products on the right, since they're highlighted in red and blue, you can see where they came from. So the first one came from a combination of the red and the blue aldehyde, where the red is the nucleophile that the enolate comes from, and the second one comes from a combination of the red and the blue nucleophile. However, the red and the blue aldehyde, where the blue acts as the enolate, and the next product is a combination of only red, where red attacks red, and then the final product is a combination of only blue, where blue attacks blue. And so this is why we can really only have, or it would be synthetically useful only to have a compound with one set of alpha hydrogens. All right, just keep in mind that these unsymmetrical aldehydes are pretty much just some carbonyl compound with alpha hydrogens reacting with another carbonyl compound. So think about what's going to happen when you have something like this. We've seen this diethylmalonate before, and we know that those alpha hydrogens are hella acidic. And so we can easily remove those with hydroxide to form an enolate. And we've got the awesome resonance stabilization with the carbonyl on the left and the right. That's what makes it so acidic. That's what makes those alpha hydrogens so acidic. And once we do that, we have a nice nucleophile that can attack an electrophile, i.e. the benzaldehyde, And so that's exactly what we're going to do. We're going to attack the benzaldehyde carbonyl carbon, and then we're going to protonate that. After we've protonated that, we've got a new, this one looks a little bit more complicated, but it's still the same beta hydroxy carbonyl, right? And so we can continue as we would and remove a proton to do the elimination to yield the new alpha beta unsaturated carbonyl compound. So we are familiar with how these diesters can react further, and so we need to remember this from previous chapters. For example, hydrolysis with H3O plus, as well as heat, does some fancy cool rearrangements, and so we'll see that a little bit later. But let's get into directed aldol reactions. So directed aldol reactions are essentially utilizing the kinetic and thermodynamic capabilities that we have, that we learned about in the previous chapters. For example, using LDA at cooler temperatures to get the kinetic product or the kinetic enolate, as well as tert butoxide to get the thermodynamic enolate. LDA being the bulky base that it is easier. It's easier for it to access the alpha hydrogen that doesn't have the methyl group, and so that's why it's the kinetic product. And so we're going to form this enolate first, and that enolate can then attack the formaldehyde, or sorry, this would be acetaldehyde, and ultimately dehydration yields this alpha beta unsaturated ketone product on the right. Now this is going to be done in sequence if necessary, and since it's done with a strong base, it's easy to isolate that enolate at 100%, and so that's what we want to do, is do the addition of the LDA first on the desired enolate or the desired carbonyl compound, and then throw in the electrophilic carbonyl compound after that. So let's try a couple practice problems, and these practice problems are going to be just a variety of the different aldols, not necessarily directed aldol, the one we just went over, but just some that are kind of interesting and fun. So this particular one right here is interesting and fun because it comes from a chemical. This particular chemical is actually obtained from turmeric root oil, and it's called artemerone, which is an absolutely terrible name, but whatever. Maybe I should have discovered it first, and I could have named it something better, perhaps. But remember, when it comes to trying to determine where these alpha beta unsaturated ketones come from, we want to look at the alpha beta unsaturated portion, and we drew that in red, and we can pretty much just determine that portion right there is going to be the carbonyl compound that got attacked. And so I drew that in red. The rest of the green can actually just be drawn in green and left as is. And so we can see that it's the ketone on the left as well as the ketone on the right that are the starting materials. And I would encourage you to try the mechanism out to determine if you actually get the final product on the left. So this next structure drawn, you can see there's a lot of similarities, right? If the beta hydroxy carbonyl compound on the bottom underwent a dehydration, we would have an alpha beta unsaturated ketone just like the one above, and so it would look even more similar. This is actually this comes from a root also, and it's the ginger root. The chemical compound is gingerol, and this one's cool because it's a beta hydroxy carbonyl, and as we drew above in all of the mechanisms, we have equilibriums occurring, and so this particular compound, if we were going to go backwards, what we would obtain is an aldehyde as well as a ketone. And that's actually what occurs when you cook ginger. The ginger breaks down into this particular ketone as well as, I presume, this aldehyde. And this is what makes it so strong, is that particular compound circled in green. And so it gets a little bit, I guess, more pungent. You can also dry the ginger and it would give it a different flavor as well. And that's because it would undergo a dehydration reaction, giving you an alpha beta unsaturated ketone, which gives it yet another different flavor. So that is, I think that's awesome because, first of all, I love ginger, love turmeric. I've been all about that golden milk lately. If you don't know about it, I mean, what else do you have to do other than make weird things that you find on the internet? Or not weird things, just like all the things. If you haven't made bread yet, then I'm just going to go ahead and say you're weird because that's like the COVID-19 thing. And then, like, what else are you making? I'm brewing, oh, dang. I'm brewing kombucha right now. And I can't wait because y'all know I love my kombucha, and I'm about to have gallons. So it's gonna be great. It's gonna be off the chain at my house. We're just gonna be, as my daughter would say, we're gonna have a bucha party. My kids love kombucha, which I think is adorable because I probably wouldn't have touched that stuff when I was a little kid, but now my daughter, she sees me grab one of those bottles, she's like, bucha, bucha. She's not even 2 yet, and I don't know. That little girl, she cray. So, I don't even, what were we talking about? Anyway, related to gingerol and artemisinin. So, I don't know about you guys, but sometimes ginger is kind of spicy, or as my son would say back in the day, feisty. Um, and if you look at the structure of this compound right here, you can see mad similarities as well. And this structure is actually the structure of capsaicin. So if you don't know, capsaicin is basically what gives peppers its spice, right? So delicious, first of all, but also definitely feisty. And I don't know, cool, right? Like it it's wild what plants will do. I mean, from one plant to the next, they all make similar things, and it's all delicious. I guess that's what we can gather. So yes, capsaicin is fire, and so is gingerol and turmeric. Check out that solid jalapeno. That jalapeno. Remember that solid joke I told you guys about? The jalapeno. It's really annoying because he's jalapeno business. Um, I don't know. Anyway, that's a bad pepper. I'm about to draw a bad crying laughing face. Oh, that was too bad. That's bad too. Let's make it stop. Make it stop. I should edit this out. And we're just gonna I'm not gonna edit this out. I'm gonna leave it for you guys to admire because it's some solid fire pepper laughing crying face. Anyway, chemistry. Drawn in green. It's pretty fun. It's practice problems. So what we have here is a diketone, and I want you to think about what's going to happen. So we've got a hydroxide, and we've got two ketones in the same molecule. So what do you think is going to happen? Well, we've been talking about removing the alpha hydrogen, right? Well, where's alpha hydrogen? Well, we've actually got lots of alpha hydrogens in this compound. We've got 4 options, at least 4 locations. And so that's going to make things interesting, right? Like, what are we going to do? So what I would suggest, try and form, this is clearly going to be an intramolecular reaction, right? And so when you have an intramolecular reaction, you want to try and form those 6-membered rings. If you can't form the 6-membered ring, you want to form the 5 or the 7 or just something that's not the most stable ring that you can. And in this case, we've got options. So we're going to form a variety of compounds, potentially. Let's see which one would probably be the best, though, or the most stable. Shazam! All right, so what I did here is I actually highlighted all of the alpha carbons with blue, pink, red, and green, and then I drew the corresponding products if you were going to remove that to form the enolate, remove the hydrogens on those alpha carbons, and form the enolate that would attack the carbonyl either on the left or the right. Now, the blue one on the left, that's crazy. It's got a bridge. That one's just all bad. It's like a 9-membered ring, and it's got a bridge with the CO that's just that hates the world, doesn't want to form. The structure in the pink, that's not bad. That's a 6-membered ring with a 5-membered ring. The structure in red, a little bit better because it's a 6-membered ring with a 5-membered ring, and that double bond is actually conjugated. The green structure on the upper right, it's conjugated, and we have a 7-membered ring. And remember, 5 and 7-membered rings are pretty similar. So the best options are going to be 5, the red and the green in terms of probable products form. Now you might be curious about the pink one. Why did we form that? Why didn't we form an alpha beta unsaturated ketone? And that's because there's no CHs to grab on at the alpha position of that from that carbonyl. And that's because it's a quaternary carbon. So that carbon only has carbon-carbon bonds and no CHs. All right, so now that we've got that covered, what we want to go over is another name reaction, which is the Claisen reaction. And this is going to be something, it's very similar. We have a carbonyl compound with alpha hydrogens. We have a base we're moving to form the enolate. And we combine those 2 carbonyl compounds to get a new carbonyl compound. But in this case, it's going to be between an ester and something else. So, for example, an ester and an ester of the same kind would yield this beta keto ester shown on the right. The presence of the H3O plus is used to quench the reaction because we still have base present. And notice the beta keto ester. This is like the acetoacetic ester, and that those hydrogens drawn in red are really acidic, and so that H3O plus is going to stop that reaction from kind of wreaking havoc or doing anything more than we want it to do. So the mechanism here from the enolate attack the carbonyl on the ester. So now the key thing and the key difference in this one is that we now have a good leaving group. So of the 3 reactions I told you to recall in the beginning, this is the last one where we have that Z group that can actually leave. So this is a nucleophilic acyl substitution. And the nucleophile is the enolate, and you're substituting that OET, the O-ethyl. Once you attack, that carbonyl compound is reformed, and the ethoxide is actually forced out as a leaving group. that ethoxide can actually come back, remove the proton from the alpha hydrogen, and then we reprotonate it with the acid. Let's try another one. So this particular ester in the presence of methoxide, noticed on the reaction above it was ethoxide with that ester with the OET, because that's ethoxide was actually the leaving group there. Now in this case we have methoxide, because methoxide is going to be our leaving group here. So anytime you have an ester, and you want to try and throw in an alkoxide that would be formed after the breakdown of that ester, so after it leaves, and that's just so you don't get a mixture of products, so you don't have any other issues. And so this particular mechanism just goes as usual, where we form the enolate. The enolate attacks the ester to form a new carbonyl compound, and now all I've done here is just kind of rearranged it so that it looks it looks prettier now, right? So this is just going to take some practice. Honestly, with the knowledge that you guys have already, you could have just probably predicted this reaction already, but it's just something that we have to kind of go over. And again, one of the reasons why I wish I was like kind of an older chemist, so that way I could have maybe had a reaction named after me, because dude just pretty much figured out a reaction that already existed and then changed it kind of a little bit. But anyway, we got this cross Claisen we got to talk about too, right? So we can do like esters and ketones, for example, where we have a ketone enolate attacking the ester, and again, that ester is going to be a good leaving group, or is the leaving group in this case, and we form a beta dicarbonyl at the end. Now, when we're doing this crossed Claisen, we can only have one set of alpha hydrogens. That's again so we don't get a mixture of products. Some of the esters that are commonly used are this ethyl chloroformate as well as the diethyl carbonate. So these are extremely reactive compounds and not super stable because they have leaving groups on either side. When it comes to the ethyl chloroformate, the chloride is going to be the better leaving group because that's the weaker conjugate base. So now let's take a look at this ester. So this particular ester in the presence of sodium methoxide, this is going to be a multi-step synthesis. So sodium methoxide with the diethyl carbonate gets you compound A. Now, after compound A is formed, we want to hit that with sodium methoxide and methyl iodide to give us compound B, and we're going to hit B with acid and heat to get us the final product, ibuprofen, which notice the carboxylic acid in the final product as opposed to the ester. All right, so enolate formation. Now we can have attack of the diethyl carbonate. Now that's going to result in a new after the loss of the ethoxide. We will get this guy. So the way I'm drawing it is obviously terrible geometry, but for the sake of keeping track of everything, I would encourage you to draw it like this. Or, I mean, if you can visualize it nice and easy, and you can put things in just where they need to be without even thinking about it, that's awesome. But for me, I like to draw the geometry, the carbon-carbon bonds just totally extended, just so that everything's not congested, and that way we can get the desired final product. So after the loss of sodium or the ethoxide, we get compound A, which has this, I circled the acidic proton at the alpha position. In that diester, we can remove that, forming an enolate, And that enolate is now the nucleophile that attacks the methyl iodide thrown and at this as the second reagent in that step. Now what we've done is we've added a methyl group to that alpha position, and now you can see it's kind of looking more or less like the final product, but we've got extra stuff on there, right? So how the heck do we get that off? We've got a lot going on. Well, this is compound B here, and notice that we have an alpha beta, we have a beta diester, and those esters, remember, can undergo hydrolysis in the presence of H3O plus, and then form carboxylic acids. After the addition of heat, we force the loss of CO2 and the formation of a carboxylic acid final product. And so that's what we do there to get that was a very complicated sequence of reagents to get to a kind of minor transformation, but it is very mild because we use that diester. It's very acidic, so we can do mild reaction conditions, and this is actually going to be really, really desirable because mild reaction conditions give us a less byproducts, and less byproducts means that we can ultimately get a product that's more pure. All right, so let's take a look at this particular structure. Let's say we wanted to know how we can make this from a Claisen reaction. Well, we see here that we got an ester and a ketone, or an aldehyde, and so what we want to do is highlight the two portions of the molecule that could have come from an ester and a ketone. Now, this could be the one I drew in blue and the one I drew in red. Either one of those could be an ester. Doesn't really matter in this case. They are pretty much the same. But no, one of them needs to be an ester and one of them needs to be a ketone, so we can form the enolate to do the attacking. And so that's a Claisen reaction via retrosynthetic analysis. So now we are moving on to the Diekman reaction. So the Diekman reaction is just intramolecular Claisen. So pretty much what we're going to be doing is forming 5 and 6 membered rings via a 1,6 or a 1,7 diester. So there's not much to discuss about this other than the fact that it's called the Diekman, and we're just pointing out its existence, so that way we're more aware when we see things like this. So this is a 1,7 diester, and throw in sodium ethoxide, and we deprotonate the alpha position, and this alpha position can then attack intramolecularly the carbonyl on the left, and that's going to give us our final product in the end. So that initial attack is going to result in a tetrahedral intermediate, and this tetrahedral intermediate is already forming the ring. So what we want to do is count all of the carbons. 1, 2, 3, 4, 5, 6. We see that the enolate carbon, or the alpha carbon, as well as the carbonyl carbon, complete 6 members of the ring. And now we want to just focus on where those are relative to one another, so that way we can draw the ester or the alkoxide portions, just to keep them there for the final product. After we lose the ethoxide, we get a ketone on the ring and then an ester coming off of it. So the way I've drawn it in red is just a little bit different than the final product on the right, upper right in black. Just flip it over and it's the same thing. That's an example of a 1,7. This would be a 1,6, and instead of a 6-membered ring, it's a 5-membered ring. Other than that, it's the same thing. All right, so now we're gonna do the Michael reaction. But so remember that time we did that thing with the alpha beta unsaturated ketone? Yes, you do, hopefully. So remember the organocuprates were weak sauce, and they actually did the conjugate addition, the 1,4 addition on the alpha beta unsaturated ketone, as opposed to Grignards and organolithiums, where they directly attack the carbonyl. So remember the alpha beta unsaturated ketone has 2 electrophilic sites. That's pretty much what I was telling you, but it's also called a Michael acceptor because this is called a Michael reaction, right? And the nucleophile attacks and the Michael acceptor accepts. So what we have is a nucleophile, generic nucleophile attacking that beta position. And then we, instead of just a generic nucleophile, why don't we just substitute in an enolate and have that attack the Michael acceptor, because that would ultimately give us a diketone. And again, we're creating a larger molecule by making more carbon-carbon bonds, which is just exactly what organic chemistry is all about. We're kind of expanding on small molecules. So some common enolates are going to be this, the diester as well as the acetoacetic ester. And remember, these are common just because they're so easy to form, because the protons are very acidic and can be done with milder conditions, which ultimately is going to lead to less side reactions. If we did this, so this alpha beta unsaturated ketone, usually in terms of like testing environment, it's usually going to be found in a ring, 2 rings, like kind of fused together like that. And so this diester is going to attack the beta position, and that's going to be resonance stabilized by the that's going to be resonance stabilized, and yeah, I'm not even going to edit that out, because that's what happens when you work in the daytime when they're awake. All right, so resonance stabilization, the CO double bond forms again, and then you protonate the alpha position with water. That leaves this fancy looking thing right here. Kind of looks like a weird face, like a cat face or a gremlin face. Remember, these diesters, esters can be hydrolyzed in the presence of acidic water, and what happens then is you form 2 carboxylic acids, right? And then once you apply the heat to those guys, you do that rearrangement, which I'll draw this time because we want to see it over and over again to get that repetition going. Shuffle the electrons around, and remember that results in the loss of 1 molecule of carbon dioxide. You form a weird looking enol, which then tautomerizes to the carboxylic acid. So notice the final product, it almost looks like the product before the hydrolysis, but that one of the esters on the left is gone, completely gone. And then obviously the ethoxide is carboxylic, is the OH now. So it should be quick and easy to jump to that final product once you kind of see a few of them. But we should also know that mechanism as well. So the Robinson annulation is the last reaction we want to go over. And annulation is referring specifically to a ring. Annulus, it means ring. I think like there's, for animal people, annulated worms, I think, or I don't know, it has something to do with rings. You also have, what is it? There's, I think with mushroom, like in terms of plants and stuff, that word probably comes up for mushrooms as well as some other, maybe leaves and stuff like that. So just remember, the Robinson annulation means that you're forming a ring. So, and you're going to do a Michael addition, then an aldol reaction to form a ring. And Sir Robert Robinson won the Nobel Prize for this because he's got almost the same name twice. And I think that was a requirement back in the day if you wanted to get the Nobel Prize for chemistry or just anything. JK. So we have a alpha beta unsaturated ketone and a cyclic ketone, and we form the enolate. We attack the beta position, boom, protonate that, right? Ultimately at the alpha position. Now we've got this ketone dangling off of this ring, this cyclic ketone, and we have an alpha hydrogen. So there's definitely more than one alpha hydrogen, right? But the one that's going to be kind of favored is the one that's going to form the six-membered ring, right? And then also we'll see in the end why this one would be favored as well, but it's the terminal methyl group that's going to be ideal. That we deprotonate that, we form the enolate, which then attacks the cyclic ketone, carbonyl carbon. And what I like to do again is count out the number of carbons, but that way I know I can quickly just draw my ring structure and then attach the rest of the groups on it. So that's what I did, draw two six-membered rings next to each other. The carbonyl group is on the bottom left, and then we have after protonation, we have the OH on the fused part where the two rings meet. This is a beta hydroxy carbonyl, right? In the presence of base, we get that deprotonation and elimination of the hydroxide. And so now we've got this ring that formed, hence Robinson annulation. And then we also have the alpha beta unsaturated ketone portion of it that we want to. Those are usually indicative of a Robinson annulation. Now I circled in green the starting material. I also highlighted the double bond because that portion, it looks exactly like the starting material except it's just missing the oxygen, right? And so this is one of the ways that I like to just quickly jump to the final product. We can break these down as the alpha beta unsaturated ketone in red and the ketone in blue. Those are going to lead to a ring with two R groups on it, right? And then we number 1, 2, 3, 4, 5, 6, and that's where the numbers come from, or that's where the numbers end up in the final product. So this should help us in quickly jumping to the final product or moving backwards when we have a alpha beta unsaturated ketone. So as your book suggests, at first you're probably going to want to orient the alpha beta unsaturated ketone as such, and then what I would do is just slice it right down that portion of the six-membered ring. It goes through the double bond and it goes through this single bond above it, and then that portion on the left of that slice is the alpha beta unsaturated ketone. And then the portion on the right is going to be the original carbonyl group. And so remember where that carbon-carbon double bond is, that's where the carbonyl group goes on the electrophilic ketone. Or I guess it's not the alpha beta unsaturated one. So which can be formed by a Robinson annulation. What we're going to do is draw out structures A, B, C, and D. I would advise you just to pause the video and try them on your own before I go over the answers. You can try, and what I would suggest is first orient them as we saw previously and see what you can get out of it. I just thought about it. My kid's yelling is kind of like having Oso in the class when he was yelling. So, brings us back to when we're all looking at each other's faces, wondering what's going on with this OChem. The good old days when everybody was healthy and happy. Hopefully you're still healthy and happy, actually, but just in a different way, and you're figuring it out, right? All right, so structure A, I arranged it as I suggested, and then we sliced down that double bond and keep going up, and then that way we can break it up into the alpha beta unsaturated ketone, and as well as the ketone on the right. So remember that carbon-carbon double bond turns into that carbon-oxygen double bond. And then we do this again for B. This one is a little bit weirder, right? It's not really, we don't have the fused ring on the right side. However, we are able to orient the alpha beta unsaturated ketone as we usually have, and that gives us a weird ring, alpha beta unsaturated ketone with a ring on it, and then we have an aldehyde. This is the last, or second to last one. It's very similar to the previous ones, and I probably wouldn't even have rearranged it, because you can just slice vertically still, and it's the same, more or less the same idea. But again, initially we want to practice this, right? So rearranging this guy, we'll notice that we have the ketone in the right spot, but we don't have the double bond in the right spot, right? So what's the problem here? Well, it's not an alpha beta unsaturated carbonyl that forms. And what does that mean? Well, that means that we can't use the Robinson annulation to form that product. All right, so let's try a couple more. Draw these bad boys out. Again, rearrange it to keep the carbonyl on the bottom left and the double bond, if it's alpha beta, just on the bottom of the ring. And then you can slice and dice. Quickly draw out your alpha beta unsaturated ketone, and then boom, draw that second ketone. One thing I want to make sure that you guys remember is that the alpha beta unsaturated ketone provides 4 carbons for that ring structure, and then the other ketone provides 2 carbons for that ring structure. So I don't want you to miss out on I feel like one of those carbons from the alpha beta unsaturated ketone can get lost, and I just want to make sure that you have that. So just draw it very suggestively. You can see that all of my structures are indicating like, hey, let's form a ring real quick, because then we'll be happy and all is great in the world, and I'll get an A on this organic chemistry test or quiz or what have you. And so that's pretty much the way I would go about doing that. I'm drawing out some homework problems for you guys to work on, and again, as always, you can choose to do them or not do them, or you can do extra. I would always suggest extra, but I know we're getting to the end of this semester, and I'm not sure how your guys' workload is, but do what you can. I think this practice right here will be sufficient, even if you have to do them maybe a couple times, but you get the gist of it. A lot of this chemistry we already know. It's just applying it in a different way. As long as you can kind of think of it that way, then I think this you guys can be super successful at this. All right. Well, also my daughter's turning 2 tomorrow. Happy birthday, Amelia, aka Amy. aka the boss. Yeah, and you are not mistaken, my son turned 4 on Saturday, so birthdays are really close together. It's cool. I mean, they had a good birthday party. Thanks for asking. That one person that gave the shout out to my son. I mean, whatever though. All right, love you guys. Bye.